Welcome to a calm journey through 6 of the universe's deepest puzzles. First, the hidden mass that shapes galaxies and clusters without ever shining. Dark matter. Before you get too comfortable, you can gently like, subscribe, or leave a comment to support the channel, and then let your attention soften as we begin with what gravity quietly reveals. In the famous bullet cluster collision, maps made from gravitational lensing show the main mass peaks sitting apart from the hottest X-ray gas, as if most of the matter sailed through the crash while the ordinary gas slammed, heated, and lagged behind, creating a vivid separation between where the light and heat are and where most of the gravity seems to be. When astronomers measure how fast stars orbit in the outer parts of spiral galaxies, the speeds often do not fall off the way they should if only the visible stars and gas provide the gravity, which suggests an extra, unseen reservoir of mass extending well beyond the bright galactic disk. Strong gravitational lensing in galaxy clusters can bend and distort the images of background galaxies so dramatically that the inferred mass distribution does not line up neatly with where most of the luminous matter sits, implying a large component of mass that does not glow the way normal matter does. Weak gravitational lensing, sometimes called cosmic shear, is subtler than giant arcs and rings, but across huge surveys it reveals a statistical pattern of tiny shape distortions in distant galaxies, allowing astronomers to map large-scale mass and showing that the universe's scaffolding is dominated by something invisible. The cosmic microwave background carries a delicate pattern of hot and cold spots, and the relative heights and spacing of those features indicate that ordinary atoms contribute only a smaller portion of the total matter budget, while a larger portion behaves like non-baryonic matter that shapes gravity without emitting light. Large-scale structure simulations reproduce the web-like clustering of galaxies most successfully when most matter is cold and non-baryonic, because that kind of matter can clump efficiently and build the gravitational framework into which ordinary gas later falls. In many merging clusters, dark matter appears effectively collisionless on large scales, because the gravitationally inferred mass can separate from collisional gas during mergers, suggesting that whatever dominates the mass does not behave like a normal fluid that shocks and heats up. Cold dark matter, meaning particles that moved slowly compared with light early in cosmic history, naturally supports a picture where small structures form first and then merge into larger ones, producing a layered hierarchy that matches many broad features of the observed cosmic web. Warm dark matter would move fast enough in the early universe to blur out some small-scale structure, so it would change expectations for how many tiny dwarf galaxy-sized halos should exist, and how sharp or smooth the smallest structures ought to be. Ultralight fuzzy dark matter is sometimes described as wave-like on galactic scales because its tiny mass can correspond to a large effective wavelength, potentially smoothing out very steep central densities and producing a different kind of small-scale granularity than particle-like models. Self-interacting dark matter models keep the idea of unseen matter but allow it to collide with itself more than standard cold dark matter does, which can gently reshape inner halo structure and may help address certain small-scale tensions without removing the dark matter concept. Modified gravity ideas attempt to explain missing mass phenomena by altering how gravity behaves at very low accelerations or large scales. But these approaches still must match a wide set of constraints, including gravitational lensing patterns and the success of cosmological models. Dark matter does not emit, absorb, or reflect light in the usual way, so astronomers cannot photograph it directly. Instead, they infer where it is by measuring how it pulls on stars, gas, and even light itself through gravitational lensing. Proposed dark matter particles include WIMPs, axions, sterile neutrinos, and other beyond standard model candidates. And the variety of candidates reflects that we see the gravitational effects clearly, while the underlying particle identity remains uncertain. Direct detection experiments are designed to catch extremely rare interactions between dark matter and ordinary matter, often placing ultra-clean detectors deep underground so that cosmic rays and other background signals are reduced as much as possible. So far, many direct detection searches have reported no confirmed dark matter interaction events, and those null results steadily tighten the range of masses and interaction strengths that common WIMP models can plausibly have. Indirect detection searches look outward for signals that might arise if dark matter annihilates or decays, such as excess gamma rays, unusual cosmic ray components, or neutrinos, and then compare those observations against astrophysical backgrounds that can mimic similar signatures. Collider searches take a different route by trying to create dark matter in high-energy particle collisions, and because the produced dark matter would slip through detectors, it would show up as missing momentum, balanced by visible particles. The tiniest dark matter halos, if they exist in large numbers, could have influenced when and where the first stars formed, because even small gravitational wells can help ordinary gas cool, gather, and ignite into early starlight. Observations of very early galaxies, especially at high redshift, may help distinguish cold, warm, and fuzzy scenarios, because each model can subtly change how quickly small halos appear and how efficiently early structures grow. Dwarf galaxies are sensitive laboratories for this mystery because they are dark matter dominated in many cases, and their internal motions, star formation histories, and shapes can reflect both dark matter physics and the complex effects of baryonic feedback. Tidal streams in the Milky Way, formed when small satellites are pulled apart, can be gently perturbed by invisible subhalos, so careful mapping of stream gaps and wiggles can offer a way to infer dark structure that contains little or no starlight. The core cusp tension compares very steep central density profiles, often seen in simple cold dark matter-only simulations, with some observations that suggest flatter inner cores in certain dwarf systems, raising questions about whether the difference comes from dark matter properties or from ordinary feedback processes. The missing satellites issue highlights that simulations can produce many more small subhalos than the number of observed luminous dwarf galaxies, which may mean many halos are dark, or that galaxy formation becomes inefficient in small halos, or that modeling details matter greatly. The too big to fail problem points to cases where the most massive predicted subhalos in simulations appear too dense compared with the observed satellites of the Milky Way, suggesting either changes in the predicted inner structure or a more complex mapping between halos and the galaxies they host. Baryonic physics can complicate dark matter inference because supernova feedback, reionization, and gas dynamics can puff up central regions, remove gas, or prevent star formation, making some halos faint or reshaped in ways that mimic changes to the dark matter itself. In modern cosmology summaries, dark matter is typically described as the majority of matter in the universe, while ordinary baryonic matter, the atoms in stars, planets, and people, makes up only a smaller fraction of the total. Within many galaxies, the dark matter halo dominates the mass budget outside the brightest stellar regions, so the outer rotation and gravitational potential are often governed more by the halo than by the luminous disk. Gravitational lensing can produce detailed mass maps, where the bright galaxies serve mainly as signposts, and the real mass distribution inferred from lensing extends well beyond what the light alone would suggest. Cluster collision speeds and reconstructed mass distributions can place limits on how strongly dark matter can self-interact, because too much self-interaction would cause the dark component to drag, heat, or spread in ways that do not match observed merger behavior. Dark matter likely helped seed structure early because ordinary baryons were coupled to radiation in the early universe and could not clump freely at first, while dark matter could begin building gravitational wells that later attracted gas after decoupling. If dark matter is made of particles, it must be stable or extraordinarily long-lived on cosmic timescales, because it remains abundant billions of years after the universe began and still shapes structure today. Warm dark matter is often characterized by a free streaming scale, meaning a distance over which its early motions smear out density fluctuations, which then reduces the formation of the smallest halos and alters the predicted small-scale population. For fuzzy dark matter, the effective de Broglie wavelength can become astrophysically large, so its wave nature can introduce a smooth central region and interference-like density patterns that differ from the granular clumps expected from heavier particles. Some models propose interactions between dark matter and dark radiation, which could leave subtle fingerprints in the cosmic microwave background and the way structures grow, blending early universe physics with late-time galaxy observations. It is possible that dark matter is not one single ingredient but multiple components, meaning that the label dark matter could refer to a family of phenomena or particles that together produce the gravitational effects we observe. Primordial black holes are sometimes discussed as a dark matter candidate in certain mass ranges because black holes formed very early could behave like dark matter gravitationally, though many observations constrain how much of dark matter could be in this form. Microlensing surveys place limits on compact object dark matter by watching for brief, characteristic brightening events when a massive object passes in front of a distant star and magnifies it through gravity. The local density of dark matter near Earth matters for direct detection expectations because the predicted event rate depends on how much dark matter flows through the solar system and how its velocity distribution is shaped by the Milky Way halo. The Milky Way's dark halo shape remains uncertain, more spherical, more flattened, or slightly triaxial, and astronomers probe it by studying stellar motions, satellite orbits, and the geometry of tidal streams that trace the galaxy's gravitational field. Galaxy clusters often have mass-to-light ratios far larger than what stellar populations alone would produce, reinforcing that most cluster mass is not carried by the stars we see, but by an unseen component dominating the gravitational potential. The standard cosmological model relies on both dark matter and dark energy. And one reason the model is so successful is that it explains diverse observations, even though the fundamental nature of both major dark components is still unknown. The gravitational influence of dark matter in clusters can also be inferred from galaxy motions using the virial theorem, where the spread of galaxy velocities reflects the depth of the gravitational potential holding the cluster together. The relative amounts of baryons and dark matter influence the acoustic peak structure in the cosmic microwave background, because baryons and dark matter respond differently to early universe pressure waves and gravitational collapse. Numerical simulations show that changing the microphysical properties of dark matter can alter halo concentrations and the abundance of substructure. So small-scale observations can act as indirect experiments testing particle-level assumptions. Some proposed dark matter interactions are so weak that, in practice, gravity might remain the only detectable handle we have, which would mean progress relies heavily on ever more precise astronomical measurements. If dark matter couples to ordinary matter through a new force, that coupling likely must be extremely feeble or act over very short distances, because otherwise it would have produced detectable signals in laboratory experiments or astrophysical systems by now. Dark matter models are constrained from many angles at once. Astrophysical dynamics, lensing, the cosmic microwave background, direct detection, indirect detection, and collider searches, and a viable model must fit across this whole web of tests. Even if a candidate particle were detected in a laboratory, demonstrating that it truly makes up the cosmic dark matter abundance would require connecting its measured properties to cosmological behavior, astrophysical distributions, and the history of structure formation. The central reason this mystery continues is that gravity reveals the presence of dark matter with striking consistency across scales. While the non-gravitational identity of the dominant component remains elusive, hidden behind silence in every ordinary band of light. Second mystery. Dark energy. The discovery that the universe's expansion is accelerating came from careful observations of distant Type Ia supernovae, whose faintness revealed that space itself has been stretching faster over time, overturning the long-held expectation that gravity alone should be slowing cosmic expansion. This acceleration implies the presence of a dominant component that acts very differently from normal matter, one that exerts a kind of outward influence on the large-scale dynamics of the universe rather than clustering into stars or galaxies. In the simplest description, this component is represented by Einstein's cosmological constant, a term he once introduced and later set aside, which behaves like a constant energy density filling space uniformly in all directions. Dark energy is often described using an equation of state parameter that relates pressure to energy density. And for a pure cosmological constant, this ratio is exactly -1, a value that naturally leads to accelerated expansion. Observational data from supernovae, the cosmic microwave background, and large galaxy surveys consistently place this ratio very close to -1, suggesting that dark energy behaves remarkably like a constant vacuum energy, though small deviations are still possible. If dark energy is not exactly constant, it could instead be a dynamic field that slowly changes over time, gently altering the expansion rate as the universe ages without producing dramatic local effects. Some speculative models even allow the equation of state value to dip below -1, which would imply unusual physics and potentially exotic future behavior, though such scenarios are tightly constrained by observations. Dark energy's influence becomes important only when the universe grows large and dilute enough that matter density drops, allowing this uniform component to dominate the overall energy balance. As dark energy takes over, it slows the growth of cosmic structure, because the accelerating expansion makes it harder for gravity to pull matter together into new galaxies and clusters. One of the key tools for tracing dark energy is the pattern of baryon acoustic oscillations, subtle ripples in galaxy distributions that act like a cosmic ruler and reveal how distances have stretched over time. Weak gravitational lensing surveys complement this by measuring how the distribution of mass bends light across cosmic history, providing clues about how structure growth has been shaped by expansion. Galaxy clusters offer another perspective, because the number of clusters that form at different times depends sensitively on both the expansion rate and the strength of gravitational growth. A deep puzzle known as the cosmological constant problem arises when simple quantum field calculations predict vacuum energy values vastly larger than what is inferred from cosmic acceleration. Closely related is the coincidence problem, which asks why dark energy begins to dominate only relatively recently in cosmic history, rather than overwhelming matter much earlier or remaining negligible forever. Dark energy also shapes the universe's long-term fate, determining whether expansion continues forever, settles into a steady pace, or evolves in more complex ways. In a universe dominated by a constant dark energy, distant galaxies will eventually recede so quickly that their light can never reach us again, gradually isolating local structures. More extreme models suggest that if dark energy strengthens over time, it could eventually tear apart bound systems, though current data do not require such dramatic outcomes. Because dark energy affects the entire geometry of the universe, precise measurements across a wide range of cosmic distances are crucial for understanding whether it changes with time. Some theories attempt to explain acceleration by modifying gravity itself on very large scales, rather than adding a new energy component. But such modifications must still match precise tests of gravity closer to home. Any successful alternative theory must reproduce general relativity's accuracy in the solar system, while deviating subtly only on cosmological scales. A difficult balance to achieve. Unlike ordinary substances, dark energy cannot be captured, compressed, or shielded, making it inaccessible to laboratory experiments and detectable only through its cosmic effects. Supernova measurements rely on careful calibration, because Type Ia supernovae are not perfectly identical but can be standardized through correlations in their light curves. Systematic uncertainties such as dust, selection effects, and calibration drift must be carefully controlled, which is why multiple independent surveys are combined. Baryon acoustic oscillations offer a geometric check that is largely independent of supernova systematics, strengthening confidence in the overall picture. The cosmic microwave background anchors the early universe, allowing astronomers to infer late-time acceleration by comparing early conditions with present-day expansion. Combining many probes helps break degeneracies between dark energy, matter density, spatial curvature, and even the masses of neutrinos. A small deviation from perfect spatial flatness could mimic some acceleration effects, which is why curvature constraints play an important supporting role. Despite its mysteries, the model with a constant cosmological constant remains remarkably successful at fitting current data across many independent observations. This success, however, does not explain why the cosmological constant has its particular small value, leaving the deeper physical origin unresolved. Some models explore interactions between dark energy and dark matter, which could subtly alter both expansion and structure formation without dramatic local signatures. If dark energy is a field, it might generate new forces, but these would have to be screened in dense regions to avoid contradicting precise local tests of gravity. Observationally, dark energy appears extremely smooth, showing no tendency to clump into structures the way matter does, even on very large scales. As the universe expands, matter density decreases, while dark energy density remains constant, naturally leading to a transition where dark energy becomes dominant. Negative pressure plays a central role in this process, because in general relativity pressure contributes to gravity, and sufficiently negative pressure drives acceleration. The realization that most of the universe's energy budget is tied up in this mysterious component reshaped cosmology and reframed many fundamental questions. Reconstructing how dark energy behaves as a function of time requires careful statistical techniques that extract information from noisy, large data sets. Small tensions between different measurements can shift inferred parameters, motivating ever more precise observations and cross-checks. Dark energy sits at the heart of precision cosmology because it affects both how far away things appear and how structures evolve over time. If dark energy truly is vacuum energy, it would connect cosmic acceleration directly to quantum physics, though in a way that remains deeply puzzling. If instead it is a new field, its potential shape determines whether acceleration continues indefinitely or eventually fades away. Cosmologists often summarize dark energy by a single parameter, representing its fraction of the total energy density today, even though that simplicity hides deep uncertainty. The same phenomenon can be described as a repulsive effect of space itself, or as a fluid with unusual pressure, depending on the chosen language. Dark energy studies rely on enormous statistical samples rather than singular dramatic events, reflecting the subtlety of its influence. Future measurements aim to detect even tiny deviations from a constant behavior, which would signal new physics beyond the simplest model. Even if no deviation is found, explaining why the cosmological constant has its observed value will remain a central challenge. Dark energy remains dark because it reveals itself only through the expansion of the universe, not through light, particles, or direct interaction. The mystery endures because multiple theoretical ideas remain consistent with current data, while the true nature of the force driving cosmic acceleration stays hidden. Third mystery: cosmic inflation and the universe's initial conditions. Inflation was proposed to explain why regions of the universe that are now vastly separated in space nevertheless share almost the same temperature and physical properties, suggesting that they were once close enough to interact before being rapidly pulled apart by an early burst of expansion. This idea also helps resolve the flatness problem, because an intense early expansion would stretch spacetime so thoroughly that any initial curvature becomes extremely difficult to detect, making the universe appear nearly flat on large scales today. Observations of the cosmic microwave background reveal a pattern of tiny temperature fluctuations whose statistical properties closely match what inflation predicts, especially a nearly scale-invariant distribution of primordial density variations. These primordial variations are thought to arise from quantum fluctuations, minute uncertainties that existed at microscopic scales and were then stretched by inflation to sizes large enough to seed galaxies and clusters. The hypothetical field, responsible for driving inflation, is often called the inflaton, and its potential energy would have dominated the universe briefly, causing spacetime itself to expand at an extraordinary rate. Different choices for the inflaton's potential lead to different detailed predictions, such as how slightly the fluctuation spectrum tilts away from perfect scale invariance, allowing observations to rule out entire families of models. One of the most sought-after signatures of inflation is a background of primordial gravitational waves, which would leave a distinctive swirling pattern in the polarization of the cosmic microwave background. Detecting these patterns is extremely challenging, because dust within our own galaxy and gravitational lensing of light can create similar signals that must be carefully separated. An early announcement of such a detection was later traced largely to galactic dust, underscoring how subtle the signal is and how careful measurements must be. As measurements improve, the absence of a detected primordial gravitational wave signal increasingly constrains inflationary models, especially those predicting very strong tensor modes. Inflation also offers an explanation for why exotic relics predicted by some high-energy theories, such as magnetic monopoles, are not observed today, because the rapid expansion would dilute them to negligible abundance. Rather than being a single theory, inflation is a broad framework containing many possible realizations, which means testing inflation often means narrowing down possibilities rather than confirming one unique mechanism. Some versions of inflation predict that once it starts, it never completely ends everywhere, leading to a picture where inflation continues in some regions while stopping in others, creating a patchwork of expanding domains. In such eternal inflation scenarios, our observable universe could be just one region among many, each potentially with different low-energy properties, an idea often associated with a multiverse. This picture raises deep questions about probability and prediction, because comparing outcomes across an effectively infinite ensemble of regions requires defining measures that are themselves controversial. When inflation ends locally, the energy driving expansion must be converted into ordinary particles and radiation in a process called reheating, which sets the stage for the hot Big Bang. The details of reheating are largely unknown, yet they matter because the temperature achieved influences particle production, dark matter abundance, and other early universe processes. The energy scale of inflation is connected to the strength of primordial gravitational waves, so tighter limits on those waves imply lower characteristic energy scales for simple inflationary models. Although inflation explains several puzzles, it does not explain why inflation began in the first place, shifting the mystery to the initial conditions that preceded the inflationary phase. In many models, inflation does not remove the need for an initial singularity, meaning questions about the ultimate beginning of space-time may still remain. Some approaches attempt to embed inflation within broader high-energy frameworks, such as string theory. But connecting those constructions to clear, testable predictions is difficult. Inflation makes specific predictions about how Gaussian the primordial fluctuations should be, and measurements so far show they are extremely close to Gaussian, restricting many complex models. Deviations from Gaussianity would signal interactions among multiple fields or non-trivial dynamics during inflation, but current limits suggest such effects are small. Simple single-field inflation models predict a consistency relation linking different observable quantities, though measuring this relation directly is extremely challenging. If more than one field was active during inflation, additional fluctuation modes could appear, but observations strongly limit such isocurvature contributions. The fact that the fluctuation spectrum is slightly tilted toward larger scales fits naturally with slow-roll inflation, where the inflaton evolves gently down its potential. Inflation must last long enough to solve the horizon and flatness problems, but the exact duration depends on the model and on how reheating unfolds afterward. Some inflationary models end through instabilities triggered by additional fields, illustrating how the exit from inflation can be as model-dependent as its onset. Other models invoke symmetries to keep the inflaton potential flat, protecting it from quantum corrections that would otherwise spoil slow, steady expansion. Modified gravity versions of inflation achieve similar expansion behavior without introducing a new scalar field, showing that inflationary dynamics can arise from different theoretical starting points. Connecting inflationary predictions to observations requires understanding how physical scales during inflation map onto the scales we see today, which depends sensitively on reheating. Separating primordial polarization signals from those generated later by gravitational lensing demands, high-resolution observations, and careful statistical delensing techniques. Some inflation models predict small features or oscillations in the fluctuation spectrum, and ongoing analyses search for these subtle imprints in cosmic data. Combining cosmic microwave background data with galaxy surveys extends the range of scales tested, improving sensitivity to inflationary physics. Inflation naturally leads to a universe that is very close to spatially flat, matching current observational limits that show only tiny allowed deviations. At its heart, inflation reframes the horizon problem as a question of causal contact, showing how regions now far apart could once have shared information before being stretched apart. The success of inflation lies partly in its ability to explain multiple puzzles at once, even though the underlying mechanism remains uncertain. Some theoretical arguments suggest that not all inflationary models are compatible with consistent quantum gravity, but these ideas are actively debated. Inflation describes how structure formed, but it does not uniquely determine why the laws of physics take their particular values, leaving room for deeper explanation. During inflation, the effective equation of state resembles that of a substance with strong negative pressure, conceptually similar to dark energy, but operating at vastly higher energies. Inflation must also avoid overproducing topological defects, unless those defects are compatible with observational limits, adding further constraints to viable models. Future polarization measurements aim to probe ever fainter signals, which could decisively support or rule out broad classes of inflationary scenarios. If primordial gravitational waves are never detected, inflation could still be correct. But favored models would shift toward lower energy or more subtle dynamics. Ultimately, inflation connects quantum physics, gravity, and cosmology. But without a full theory of quantum gravity, its deepest foundations remain incomplete. The enduring mystery is that inflation fits the data remarkably well, while leaving open fundamental questions about its origin, uniqueness, and connection to the earliest moments of space-time. Fourth mystery: black hole information and quantum horizons. Black holes introduce a deep puzzle because calculations combining gravity and quantum theory suggest they emit a faint thermal glow, now known as Hawking radiation, which slowly carries energy away and implies that black holes are not perfectly black, but can evaporate over immense spans of time. This radiation appears almost completely random, carrying no obvious record of the complex matter and radiation that originally fell into the black hole, which creates tension with the quantum principle that information should never be truly destroyed. The paradox becomes especially sharp if a black hole forms from a well-defined quantum state and then evaporates entirely, because the final state of featureless radiation seems unable to encode the detailed information of the initial state. Black hole entropy, described by the Bekenstein-Hawking formula, scales with the surface area of the event horizon rather than the volume, hinting that the information content of a region of space may be encoded on its boundary. This area-based scaling was one of the first clues that gravity, thermodynamics, and quantum information are deeply intertwined, suggesting that space-time itself may have an underlying informational structure. The expected evolution of information during black hole evaporation is often summarized by the Page curve, which predicts that the entanglement entropy of the radiation first rises and then falls if information is ultimately preserved. Early in evaporation, Hawking radiation appears nearly thermal and uncorrelated. But after a certain point known as the Page time, later radiation should become increasingly correlated with earlier radiation if unitarity holds. The firewall argument sharpened the paradox by showing that three seemingly reasonable assumptions, smooth horizons, quantum unitarity, and local quantum field theory, cannot all be true at the same time. According to this argument, preserving information and standard quantum mechanics might require violent, high-energy phenomena at the event horizon, contradicting the expectation that crossing the horizon of a large black hole should feel uneventful. Black hole complementarity attempts to resolve this by suggesting that no single observer can witness all aspects of the paradox at once, though precisely how this avoids contradictions remains subtle. Holographic duality provides a powerful perspective by showing that certain gravitational systems are equivalent to ordinary quantum systems without gravity, in which information is manifestly preserved. In this picture, processes inside a black hole can be mapped to well-defined quantum dynamics on a lower dimensional boundary, offering a framework where evaporation is unitary. However, this duality is best understood in space-times unlike our own universe, making it challenging to translate the lessons directly to realistic astrophysical black holes. Recent developments involving islands in entropy calculations suggest that parts of the black hole interior should be counted as belonging to the radiation's quantum description, dramatically altering entropy predictions. These island calculations successfully reproduce a Page-like curve in simplified models, indicating that semi-classical gravity must be applied more carefully when quantum entanglement is involved. The appearance of islands suggests that information thought to be trapped behind the horizon may be encoded non-locally in the radiation far away. Despite their conceptual power, island results are most robust in lower dimensional or highly idealized settings, and extending them fully to four-dimensional black holes remains an active area of research. Hawking radiation from stellar mass black holes is extraordinarily weak, making direct experimental tests of information recovery effectively impossible with current or foreseeable technology. Laboratory analogues, such as sonic horizons in fluids, can mimic aspects of Hawking radiation, but they cannot reproduce the full gravitational and informational structure of real black holes. The finite entropy of a black hole implies that it corresponds to a finite number of microscopic states, reinforcing the idea that black holes are ordinary quantum systems in disguise. String theory has successfully counted microstates for certain idealized black holes, matching the expected entropy and lending support to the idea that information is stored in detailed quantum configurations. If information were truly lost in black hole evaporation, it would require modifying quantum mechanics itself, or accepting non-unitary evolution, which would have profound consequences far beyond black holes. One alternative idea is that information escapes subtly encoded in extremely fine correlations within Hawking radiation, invisible at coarse scales but present in principle. Another proposal involves long-lived remnants that store information after evaporation. Though such remnants raise problems like infinite state densities and uncontrolled production, the firewall proposal challenges the equivalence principle by suggesting that an infalling observer might encounter extreme phenomena at the horizon. Contradicting classical expectations, general relativity predicts that a freely falling observer should cross the horizon of a sufficiently large black hole without noticing anything special at that location. A key subtlety is that no observer can both collect all the early radiation far away and then also easily fall into the black hole, complicating how contradictions are operationally defined. Entanglement lies at the heart of the paradox. Because Hawking radiation is produced in correlated pairs, straddling the horizon, linking interior and exterior regions. Quantum monogamy limits how strongly one system can be entangled with multiple others, which drives the tension between smooth horizons and information recovery. Ideas from quantum error correction have entered the discussion, suggesting that space-time regions may be redundantly encoded in a way that protects information despite apparent loss. The conjecture known as ER equals EPR links entanglement with space-time connectivity, proposing that quantum correlations may be geometrically represented as wormhole-like structures. The classical no hair principle states that black holes are fully described by mass, charge, and spin, which seems insufficient to encode the rich details of everything that falls in. This simplicity at the macroscopic level does not preclude enormous microscopic complexity. Much like a thermodynamic system can be described by a few variables while containing vast microstate information. Inside black holes, classical general relativity predicts singularities where known physical laws break down, signaling the need for quantum gravity. If quantum gravity resolves singularities, it may also alter horizon behavior and change how information is stored and released. The paradox depends critically on assuming local quantum field theory near the horizon, an assumption that may fail in subtle ways when gravity becomes fully quantum. The timescale for black hole evaporation grows rapidly with mass, so stellar mass black holes will not evaporate meaningfully for times far exceeding the current age of the universe. Even so, the paradox matters because it tests the internal consistency of fundamental principles. Not because of immediate observational relevance. Quantum extremal surfaces generalize classical geometric constructions and play a key role in modern entropy calculations involving black holes. These surfaces help determine which regions contribute to entanglement, entropy, and reveal surprising connections between geometry and information. The information problem connects to broader questions about observables and time in quantum gravity, because horizons limit what can be measured and compared. If information is preserved, Hawking radiation must deviate from perfect thermality at an exquisitely fine-grained level, encoding subtle correlations. Such deviations may be practically undetectable, meaning the resolution of the paradox could remain largely theoretical. The study of black hole information has driven fruitful exchanges between gravity, quantum theory, and information science, enriching all three fields. Hawking's discovery that black holes have temperature transformed them from purely classical objects into thermodynamic systems. Black hole thermodynamics includes laws resembling those of ordinary thermodynamics, with horizon area playing a role analogous to entropy. The generalized second law suggests that total entropy, including black hole entropy, never decreases, hinting at deep underlying consistency. Any complete theory of quantum gravity must explain black hole entropy and information flow in a unified and universal way. Different proposed resolutions place new physics at the horizon, at the singularity, or in non-local connections across space-time. No single resolution has achieved universal acceptance, reflecting the depth of the conceptual challenge. Black hole information remains one of the clearest windows into the structure of quantum gravity, where the nature of space-time itself is called into question. Fifth mystery: quantum gravity and the theory of everything. Gravity is described with extraordinary accuracy by general relativity, while the other fundamental forces are described by quantum mechanics. Yet these two frameworks are built on incompatible assumptions that clash in extreme environments like black holes and the earliest moments of the universe. A quantum theory of gravity is widely expected to be essential for understanding regions where space-time curvature becomes extreme, because classical descriptions break down and quantum effects can no longer be ignored. One of the main challenges in developing quantum gravity is the lack of direct experimental guidance, since quantum gravitational effects are expected to be incredibly weak at energies we can currently probe. String theory approaches this challenge by replacing point-like particles with tiny vibrating strings, whose different vibration modes correspond to different particles, including one that naturally behaves like a graviton. Because strings require additional spatial dimensions to be mathematically consistent, string theory predicts extra dimensions beyond the familiar three, which must be compactified or hidden at very small scales. The vast number of ways these extra dimensions can be arranged leads to a large landscape of possible low-energy physical laws, making it difficult to extract unique predictions. Loop quantum gravity takes a different route by attempting to quantize spacetime itself, treating geometry as something made of discrete quantum elements rather than a smooth continuum. In this picture, areas and volumes come in discrete units, suggesting that spacetime has an atomic-like structure at the smallest scales. Spin foam models extend this idea by describing how these quantum geometric elements evolve, forming a history of spacetime built from interconnected quantum processes. Causal set theory proposes that spacetime is fundamentally a collection of discrete events ordered by causality, with the familiar smooth geometry emerging only at large scales. Causal dynamical triangulations construct spacetime from simple building blocks while preserving causality, and numerical simulations suggest that a smooth four-dimensional universe can emerge from this approach. Asymptotic safety explores the possibility that gravity becomes well-behaved at very high energies due to a special fixed point, allowing a predictive quantum theory without introducing entirely new ingredients. Emergent gravity ideas suggest that spacetime and gravity may not be fundamental at all, but instead arise from deeper quantum degrees of freedom, somewhat like fluid behavior emerges from molecular interactions. Holographic principles imply that the physics inside a region of space can be fully described by information on its boundary, radically reshaping how space, gravity, and information are understood. Despite their differences, all quantum gravity approaches must recover ordinary general relativity at large scales, where gravity behaves classically and space-time appears smooth. they must also reproduce the successes of quantum field theory in regimes where gravity is weak, maintaining consistency with particle physics experiments. A major technical obstacle is that straightforward attempts to quantize general relativity lead to uncontrollable infinities, motivating alternative formulations or entirely new frameworks. Beyond technical issues, there is a deep conceptual problem with time. Because in general relativity, time is dynamic and observer-dependent, while in quantum mechanics, it is usually treated as an external parameter. This leads to the so-called problem of time, where defining evolution and change becomes subtle when space-time itself is subject to quantum uncertainty. Some approaches suggest that time may emerge from correlations between quantum subsystems rather than existing as a fundamental background quantity. Quantum gravity is often expected to introduce a minimum length scale, near the Planck length, below which the concept of distance loses its classical meaning. Such a minimum scale could modify notions of locality and causality, potentially reshaping how interactions propagate at the smallest distances. High-energy astrophysical observations, such as gamma-ray bursts, are sometimes examined for tiny violations of Lorentz symmetry that might hint at quantum spacetime structure. The early universe provides another potential testing ground, because quantum gravitational effects may have influenced inflation, primordial fluctuations, or the resolution of the initial singularity. Some loop quantum cosmology models replace the Big Bang with a bounce, suggesting that the universe may have emerged from a prior contracting phase. String theory has had success reproducing black hole entropy in certain idealized cases, offering insight into how microscopic degrees of freedom account for gravitational thermodynamics. A complete quantum gravity theory should explain black hole information flow and entropy for generic black holes, not just special symmetric examples. It should also clarify whether information is always preserved and how apparent non-locality near horizons is reconciled with everyday locality. Quantum gravity research often relies on advanced mathematics, which can make physical interpretation difficult even when formal progress is made. The enormous energy gap between accessible experiments and the Planck scale means that indirect tests and consistency checks play an outsized role. Gravitational wave astronomy opens a new window on strong gravity, but current observations still probe regimes where classical general relativity works extremely well. Some speculative ideas predict subtle echoes or deviations in black hole merger signals, though no conclusive evidence has yet emerged. A long-standing goal of quantum gravity is unification. The idea that gravity and the other forces arise from a single underlying framework. Historical successes in unifying electricity and magnetism, and later the electroweak force, motivate the hope that gravity can also be brought into a unified picture. Grand unified theories address the non-gravitational forces, but typically do not include quantum gravity, leaving it as the final missing piece. Because data do not yet favor one approach decisively, the field remains diverse, with multiple competing frameworks developing in parallel. Some researchers focus on identifying shared principles across approaches, such as holography or the central role of entanglement, rather than committing to a single formalism. Any successful theory must explain why space-time looks classical and continuous at human scales, despite being quantum at the smallest scales. It must also explain why quantum field theory on curved space-time works so well in most observed situations. Many approaches suggest that entanglement may be the glue that holds space-time together, linking quantum information directly to geometry. Despite decades of work, quantum gravity remains under-constrained by experiment, meaning theoretical elegance alone cannot determine the correct path. The absence of decisive observational signatures is a major reason the field has not converged on a single accepted theory. Quantum gravity may ultimately help explain why the cosmological constant is so small compared with naive quantum expectations. Even defining what counts as a physical observable in a fully quantum spacetime remains subtle because of gauge freedom and diffeomorphism invariance. The persistence of this mystery reflects the fact that gravity governs the structure of the universe, while quantum theory governs its smallest constituents, and bringing them together challenges our deepest assumptions about reality. Sixth mystery: the Fermi paradox and the silence of the galaxy. The Fermi paradox arises from a simple and unsettling contrast. The Milky Way contains hundreds of billions of stars and countless planets. Yet, despite decades of searching, there is no confirmed evidence of advanced extraterrestrial civilizations. This tension is often framed by the Drake equation, which breaks the problem into factors such as how often stars form, how many have planets, how many planets could host life, and how long technological civilizations might last, revealing just how many uncertainties compound together. Even if planets suitable for life are common, the steps from basic chemistry to living cells, from single-celled organisms to complex life, and from intelligence to technology may each be rare bottlenecks. The idea known as the Great Filter suggests that at least one of these steps is extremely unlikely, drastically reducing the number of civilizations that become visible on cosmic scales. If the Great Filter lies in the distant past, it could mean that the emergence of complex life or intelligence is extraordinarily rare, making Earth a profound exception rather than a typical example. If the Great Filter lies ahead, it could mean that technological civilizations tend to self-destruct, stagnate, or otherwise fail to persist long enough to spread or communicate widely. Some hypotheses propose that advanced civilizations deliberately avoid contact, choosing to observe quietly or hide their presence for ethical, safety, or cultural reasons. Related ideas suggest that civilizations remain silent out of caution, reasoning that broadcasting their existence could attract hostile attention in a potentially dangerous cosmic environment. Another possibility is that interstellar travel is far more difficult, expensive, or unattractive than often assumed, reducing the likelihood of galaxy-wide expansion. Even if travel is physically possible, civilizations may not prioritize colonization, instead focusing on local stability, sustainability, or internal development. Communication itself may be a limiting factor, because civilizations could use technologies that are tightly beamed, short-lived, or fundamentally different from those we are searching for. Early searches focused heavily on radio signals, but advanced societies might quickly move beyond radio to more efficient or less detectable forms of communication. Modern searches now include optical and infrared signals, looking for laser flashes or unusual heat signatures. But these searches still cover only a tiny fraction of the possible signal space. Non-detections do not necessarily imply absence, because a civilization's broadcasting phase could be brief compared with cosmic timescales. Signals could also be intermittent, directional, or rare, making detection a matter of timing as much as sensitivity. Some civilizations might be extremely energy efficient, producing little waste heat or electromagnetic leakage, that would stand out against natural astrophysical sources. Searches for large-scale engineering, such as hypothetical megastructures that capture stellar energy, have not found convincing examples so far. The rare Earth perspective argues that while microbial life may be common, complex multicellular life requires a long chain of favorable conditions that seldom align. Factors such as stable climates, plate tectonics, magnetic fields, and large moons may all contribute to long-term habitability in ways that are not guaranteed. Stellar environments also matter, because frequent flares or intense radiation from some stars could hinder the development of surface life without strong protection. Life might commonly exist in subsurface oceans or deep environments where technology based on fire, electricity, or radio is unlikely to arise. Intelligence does not automatically lead to technology, as shown on Earth by intelligent species that never developed industrial civilizations. Even technological intelligence may not lead to spacefaring or communicative behavior if environmental or social pressures push in other directions. Colonization arguments often assume rapid exponential growth, but real-world constraints can slow or halt expansion over long timescales. Motivation plays a key role, because a civilization with no interest in expansion will not fill the galaxy even if it could. Some scenarios suggest civilizations may retreat into virtual worlds, minimizing physical activity and leaving little trace detectable from afar. Interstellar signals must also travel through the interstellar medium, where dispersion, scattering, and absorption can distort or weaken them. From our perspective, the region of parameter space we have searched, the frequencies, times, directions, and signal types, is still vanishingly small. Many potential technosignatures could be transient, such as brief bursts or short-lived artifacts, which are easy to miss. Occasional unexplained signals have been detected, but without repeatability they cannot be confirmed as artificial. The absence of obvious artifacts in the solar system does not rule out past or distant visitors, because thorough searches are limited and ongoing. Some proposals suggest small probes rather than crewed missions, which would be harder to detect and easier to overlook. Speculative ideas about dormant probes or lurkers remain unproven, highlighting how incomplete our local search still is. Civilizations might rise and fall over cosmic history, leaving little overlap in time for mutual detection. If most civilizations are short-lived, the galaxy could host many isolated episodes of intelligence without sustained communication. It is also possible that humanity is early, emerging before most other technological civilizations have had time to arise. Conversely, humanity could be late, with earlier civilizations having vanished long ago, leaving subtle or eroded traces. Catastrophic cosmic events, such as nearby supernovae or gamma-ray bursts, could periodically reset biological progress in large regions of the galaxy. Habitability may therefore be unevenly distributed in both space and time, rather than steadily increasing everywhere. The paradox is shaped not only by astrophysics and biology, but also by assumptions about behavior, culture, and long-term planning. Our intuition about what civilizations should do may reflect human history more than universal patterns. As searches expand to include biosignatures in exoplanet atmospheres, we may find evidence of life without technology, reshaping the question rather than answering it. Detecting simple life would not resolve the silence of advanced civilizations, but it would clarify where the filters might lie. The Fermi paradox remains open, because every proposed explanation fits some facts while leaving others unresolved. In the quiet of the night sky, the absence of clear signals does not speak of emptiness so much as vast uncertainty. The galaxy may be filled with life that is distant, quiet, brief, hidden, or simply different from what we expect. And so the silence itself becomes part of the mystery, inviting patience, humility, and a gentle awareness of how little we truly know as the universe drifts on.